Hello, this is our review session for Exam 5, Chem 112. Now this is going to cover some of the chapters that's on the syllabus, like chapter 14, 16, 17, and 20, 12th edition of Brown and LeMay book. And basically that would cover kinetics, equilibrium, pH, voltaic cell, electrolysis. So I'll go over sample problems and make sure you understand those problems and try to find similar problems from the book, because that would help you to do well in exam. So my first practice problem is on kinetics. Kinetics means rate of reaction. So this is practice number 1. This is review 5, Chem 112. Now this problem I took from the book, so if you have 12th edition book, that would be number 25, chapter 14. So number 14.25. And they're referring to this reaction, 2H2 plus oxygen that yields 2H2O gas. And what they're saying is hydrogen is burning. This is given. Hydrogen is burning at the rate of 0.48 mole per second. Mole per second. So that's the rate at which hydrogen is burning, 0.48 mole per second. Question is, what is the rate of consumption of oxygen? Even though this particular question is asking for rate of consumption of oxygen, I can ask you rate of formation of water. But once you understand this, you should be able to do the other related problems. So let me show you how I can do this problem. First, rate of burning of hydrogen. I can write it down. Rate of burning means, again, this reaction is happening, so the concentration of hydrogen is going down. So delta H2 over delta T. Now why there is negative? Because the reactant, as the reaction goes on, the concentration goes down. So whenever you write down rate of a reactant, there should be negative sign. That means that's the declining function. Concentration is decreasing with time. Our final concentration is less than the initial concentration because they are being used up in the chemical reaction. Okay, now I can first set up something like this. Now whenever you see coefficient 2, divide by 2. That way I can set it equal to that of oxygen rate minus delta O2 by delta T. Again, it's inverse of 1 because I have 1 here. So let's write down these coefficients, 2, 1, 2. If I want to write down in terms of products, I'll write down 1 over 2. Now this time it's not, it's going to be positive because the product delta H2O by delta T. Now why we divided this by 2? Because if you think about the rate of oxygen disappearance or dissipation, this is going to be half of that rate, because in order to set them equal, because this is already going at a rate of 2 molecules of H2, each time one molecule of oxygen reacts. So in order to set them equal, 2 equals to 1, we know that we cannot set 2 equals to 1. So divide 2 by 2. So this is 2, so divide by 2. So that's why you divide this by 2 and then set it equal to that of oxygen. And in this particular question, we only need to deal with these two. So let's write down this value. Hydrogen is burning. Burning means this value is given. Delta H2 by delta T minus delta H2 by delta T. And that value is 0.48. So let's have half times 0.48, that's mole per second, and that's equal to that of oxygen, minus delta O2 by delta T. So minus delta H2 by delta T is equal to 0.48 because that's the rate at which hydrogen is burning. And you take half of that because hydrogen is already disappearing 2 times faster than oxygen. So to set them equal, we'll have to divide by 2, and that's why we divided by 2. And our final answer for this is 0.24 mole per second. And that's the rate at which oxygen is being consumed. So consumption rate of oxygen is 0.24 mole per second. So there could be several different wording often used here. Dissipation of oxygen or consumption of oxygen, they all mean the same thing. So this is our practice problem number 1. Let's try practice problem number 2 now. Now this problem, let me first write down what is given information. So given information, concentration of A, well, let's assume that I have a reaction like this, A giving products. A could be a reactant, any reactant that gives you products, and the given, that is a second order reaction. Second order. Not only that, it says that concentration of A drops. As time goes on, it drops from 0.10 molar to 0.025. The question is, oh, this is the time. Whole thing happens in 5 seconds. So we want rate constant. So it's given that reactant A gives products and it's a second order reaction. In 5 seconds, concentration of A drops from 0.10 to 0.025. And what is the rate constant? Now, this is how you should be thinking about this problem. First thing is the second order reaction. So you think in terms of all the equations that you know about second order reaction. Not only that, we're dealing with 2 different concentrations. Initial value, what we can write down as A0. Let's write down A0 for initial, and that value is 0.10 molar. AT is the final concentration after that 5 seconds, and that value is 0.025. 0.025, and time is given, which is 5 seconds. So from the word problem, I can write down like this. That allows me to think better. So your equations that you'll be looking for must include A0 and AT in that expression. And for second order reaction, we know this expression. So before the test, make sure you bring in all these equations, and that would help you to quickly find out what equation to use. And this is equals to 1 over A0 plus KT. So this is the expression for second order. And keep in mind that first order expression is quite different. That is log of AT by A0, and then equals to KT. Minus KT. So in this case, this is inverse of AT, inverse of A0, inverse of final concentration, inverse of initial concentration, K times T. Now let's plug in all these numbers that is given. So 1 over 0.025 equals to 1 over initial value 0.10 plus K, that's what we need to find out, and then 6 second, so I'm sorry, 5 second, so it'd be 5.0 second. And then you solve for K, and by the way, these are all molarity, 0.025 molar. So it's a molarity, this is the inverse of molarity. And after doing all this math, this is what you get. K equals to 6.0 per molarity per second. So this is the answer to this question. Let me have a quick review of what we did. This is given. This is for a second order reaction. Concentration of reactant drops from 0.10 to 0.025 in 5 seconds. What is the rate constant? So we identified this equation for second order reaction, which it has both A0 and AT, and then we plugged in our numbers and we got our answer. So that's our practice problem number 2. We should select another problem like this, which I'm calling it practice number 3. I can have a variation of my question in such a way, like in this case, for example, initial concentration is given. Maybe I would not give you initial concentration. I'll give you final concentration time and rate constant. Still, you should be able to use the same expression to get initial concentration. Or I may not give you final concentration, but I would give you A0, K, as well as T. So it'd be just a simple algebra. So make sure you try those kind of problems. Say K is given, just for your practice. Say K is given. Say final concentration is given. Let's assume some of these numbers. Time is given. So the question is how to get A0. So try problems like these. That way you feel more comfortable in solving this kind of problems. Our next 2 problems are tied together because I've selected one problem from the book, and you'd get similar question in exam. Of course, I'll give you different data. So this is going to be 3 and 4. I think that this will be 4 and 5. So practice 4, 5. Now the problem that I picked, this is how I should write down a title for this kind of calculation. Calculation of order, rate constant calculation. So order, once you know the order of reaction and rate constant, you can calculate what we call rate law. So that's what we're going to learn by doing this practice problem. And for that I selected number 14.34 from Brown-Lemay book, 12th edition book, from chapter 14. So let me just write down the reaction. 2ClO2 minus plus 2OH minus giving products. I'm not writing down all the products because it's not necessary to write down, because rate only depends upon these concentrations. Now these are the experimental data given in this problem. Experimental data, and ClO2 minus concentration in the second row, second column. Then OH minus concentration is all in molarity, and rate is given in the last column. So let's now write down the 3 experimental data given, 1, 2, and 3, and I'm going to write down these values: 0.060 for the first experiment, 0.020 for the second experiment, 0.020 for the third experiment. With OH minus concentration, it's 0.030, 0.030, 0.090. Okay, so that's 3. And the rate values 0.0248, 0.0248, 0.00276, and then 0.00828. Okay. Now, question is, with all the given information, we need to get rate law. So what is rate law? It's basically referring to this rate expression. Rate is given by a rate constant times concentration of reactant O2 minus raised to the power A. A is the order of reaction with respect to ClO2 minus, which we don't know yet. That's why you have A. And then OH minus raised to the power B. That's the order of reaction with respect to OH minus. So basically we need to know this A value, B value, and K value, and then you can plug in any concentration values and you can get the rate of reaction. And that's why it's called rate law. So let's first find out A and B values. These are the three set of data that we have, and that would allow us to get A or B values. Now what I'm going to do first is I'm going to take rate 1. This is rate 1 for experiment 1. So we call it rate 1. Let's write down here. This is rate 1. This is rate 2. This is rate 3, or rate for experiment 1. So rate for experiment 1 divided by rate for experiment 2 equals to 0.0248 divided by 0.00276. That's basically the last column. But keep in mind, rate would be given by the product, these two products. So I'm going to write on that next. So the K, which you don't know at this time, times ClO2 concentration, the top one is rate 1, so 0.060, 0.060, raised to the power A, then OH minus 0.030, 30, raised to the power B. At the bottom, again that's coming from rate 2, this is the rate 2 data set. So ClK times ClO2 minus would be 0.020 raised to the power A, and 0.030 raised to the power B. Okay, K would cancel out, 0.030 B would cancel out. So only thing left is here. That's and let me write down what you got here. This I get 9 equals to 3 to the power A. This is 3. Now, you know that 9 can be written down as 3 squared equals to 3 to the power A. So basically, that gives you A equals to 2. So order of reaction with respect to ClO2 minus is 2. So we already got one order. Now in next step, again you select the two other rates in such a way that this time A would cancel out, but B would not cancel out. So in last case, B canceled out because we selected it that way. And in doing that, I'm just going to tell you that what you're going to select here, rate 3 by rate 2. So if I have, let me write down here, rate 3 over rate 2. So this is rate 3 over rate 2. Again, in the same way you can do the math, and that's what you're going to get is the following. 3 equals to 3 to the power B. So this is 3 means 3 to the power 1. So make sure you try this, and that gives you B equals to 1. So basically rate 3, this is the rate 3, 0.0828. This is rate 2, 0.0276. And this is rate 3. And then you have all these concentrations. you can see that 0.020, 0.020 cancel out, but this would not cancel out, and that would have b. And that's how we get 3 to the power b. Make sure you try that and see how that works out. So I now got this rate law one step ahead. I can now write it down as ClO2 minus raised to the power 2 and OH minus raised to the power 1. Next step, I need to get the rate constant. Now, that will be straightforward now. Once I got this rate value, you can plug in any of the rate expressions. So let me show you how. So I'm going to get more space here. Do it like this. Select any rate. Say I'm taking this, rate 1. Rate 1 equals to 0.0248 equals to rate constant. This time I know the order of reaction times ClO2 raised to the power 2 and OH minus raised to the power 1. Now we're calculating rate constant, so just use the rate 1, all this data for rate 1. So K times ClO2 minus is 0.060 to the power 2 and OH minus is 0.030. And then you can solve for K. 0.0248 divided by 0.060, and this is 0.030 raised to the power 1. So make sure you do this math, and that will give you your final K value. So you should write down this answer. Now, we have 3 sets of data, so there should be 3 K values. So you can always get the average. And that would be the average rate constant. And so an exam would be specific about your values, what we want you to calculate. We'd ask you to calculate order of reaction with respect to reactant 1, with respect to reactant 2, or a rate constant for the whole reaction. And overall order of the reaction is 2 plus 1, 3. Overall order is third order reaction. So make sure you also understand that. Okay, so this includes calculation of 2 orders of reaction. One is for ClO2 minus, the other one is OH minus. And also we need the third calculation on rate constant. Now, let's now go over practice problem number 6. Now this will be on general understanding of topic. This will be on general understanding of topics. Like, I'll give you just a simple example. In acidic solution, will is this true? Quite often we think that we have acidic solution means there is no OH minus concentration. So in acidic solution, would it mean that there is no OH minus in the solution, in aqueous solution? Answer is no. This is wrong. Always there will be some OH minus in the solution. So this has to be maintained all the time. H plus times OH minus equals to 1.0 times 10 to the negative 14. That's water dissociation constant. So no matter what H plus you have, you must have OH concentration in such a way so that the product is 10 to the negative 14. So keep that in mind. Having acidic solution doesn't mean absence of OH minus. Other thing I have, H plus concentration is same as H3O plus concentration in water, because water is going to grab H plus, and that would be loose H plus. That would be given off whenever anything needs H plus. So sometimes we write down H plus, sometimes we write down as H3O plus. Keep in mind that that's the same thing. Also, if I have H3O plus concentration exceeding that of OH minus concentration, you would expect an acidic solution. So basically, in an acidic solution, you'd expect more H plus than OH minus. On the other hand, for a basic solution, it's just the opposite. You get more OH minus concentration than H3O plus. So that gives you a basic solution. So it's never an absence of the other. So keep that in mind. And also, in acidic solution, we all know that pH, in terms of pH, is less than 7. For basic, it's more than 7. Equal to 7 means it's neutral as long as we have room temperature. Room temperature means 25 degrees centigrade. So there could be a question on these understanding. That's practice number 6. Now practice number 7, that's problem number 7. Again, that would be general understanding issue. That means pOH values. We often get confused with pH and pOH values. How are they related to H plus or OH minus concentration? Say I'm giving pOH. I'm giving you 3 different solutions with pOH values of 5, 7, and 9. If I want to find out which one is most acidic, so this is solution 1 having pOH 5, solution 2 pOH 7, solution 3 with pOH 9. Now quite often we get confused when I look at these pOH and pH. So if you feel more comfortable, change it to pH. By knowing this expression, pH plus pOH equals to 14. This always is the case in water solution. So when pOH value is given, so let's calculate corresponding pH for solution 1. 14 minus 5, so that would give me 9. For solution 1, for solution 2, pH is going to be 14 minus 7, that's 7. For solution 3, pH is going to be 14 minus 9, that's 5. Because I would like you to think in terms of either pH or pOH. More acidic means a smaller and smaller pH value, because that's how we define it, minus log of H plus or log of inverse of H plus. So this is most acidic among these 3 solutions. The solution number 3 is the most acidic. Which one is most basic? This one, pH 9 or pO. Or of course you can see that the reverse way can talk in terms of pOH. Now practice number 8. I'll give you a series of compounds, say a series of bases, just for our practice. is given, I'll give you calcium. If I give you calcium hydroxide, ammonia, and this is called methylamine, CH3NH2. If I ask you, which one is the strongest base? So this would also fall under general understanding. Most group 1A and 2A hydroxides are strong bases. That means they 100% dissociate. So sodium, potassium, calcium. Magnesium doesn't show that kind of behavior, but other than that, almost all group 1A and most of the group 2A elements show 100% breakdown. So they're all strong bases. So this would be the strongest base. Ammonia is a weak base. Methylamine is also a weak base. So the strongest would be calcium hydroxide. So I may give you series of bases, series of acids. So this is our practice 8. Practice number 9. So you don't need to really do math problem or solve anything when you have a question like this. Series of acids. I can give you a series of acids and you need to find out the strongest acid. For example, I can give you H2CO3, for example. So in my lecture note, I have series of different strong acids. If I were you, I'll remember only the strong acids. All other acids would be weak acids. So for example, just for this example, HCl, H2CO3 and HCl. Which one is the strongest acid? HCl. So I need to know which acids are the strongest acid. There are not too many in number, like HCl, HBr, HI, HNO3. These are strong acids. So look at that lecture note. You see the list of acids. Book also has them. Then H2CO3 is a weak acid. So there will be a question like this where you just need to know which one is the strong acid. Then this is our practice number 9. It's still on general understanding. Now we're going to do practice number 10. So that's practice number 10. Say I'm going to write down 3 different samples and their Ka values. So I have, say, one sample solution has Ka equals to 1.1 times 10 to the negative 5. And I have sample 2 with Ka value of 1.3 times 10 to the negative 6. And sample 3 has Ka equals to 1.5 times 10 to the negative 7. So question would be the following. Strongest, which one is the strongest base? And which of the is weakest base? Now, if it is a Ka, first let's talk about the Ka and Kb. If I had Kb values, then we can talk about the strongest base based on Kb values. Now here, since I wrote down all the Ka values, it should be the strongest acid. Let's write down the strongest acid and weakest acid. The largest Ka value would mean you got the largest quantity of products. That means that particular Ka would represent most H plus breaking down. And that would be the strongest acid, because acid means the substance that gives up H plus. So this would give you maximum H plus. So I would say solution 1 is the strongest acid solution. The weakest one would be the one which has the smallest value of Ka, which would be solution 3. On the other hand, if I had Kb values, the largest Kb would have largest quantity of OH minus, and the smallest Kb value would be the weakest base. Now we're going to do practice problem number 11. Now, this is going to be a quantitative problem. That's practice number 11. This is on percent ionization. Percent ionization of a weak acid. I may give you similar question, may not be exactly this acid, it could be another acid, but once you understand these, you should be able to do that problem. And again, I picked this problem from the book, which is number 16.63. Brown and LeMay, 12th edition. Let me write down that compound. HN3. From the formula, you know that this is not a strong acid. It's not like one of those known acids like HCl, HBr, HI. This is HN3. That would break down into H plus plus N3 minus. Now, what is given in this case? Initial concentrations. Initial concentrations is 0.400 of this weak acid, 0.400 molar. And I didn't have an H plus or an N3 minus at the beginning. At equilibrium, since this is a weak acid, 100% would not break down. Only part of this would break down. If I say that X of this broke down to H plus and N3 minus, then left over would be 0.400 minus X. Then how much of H plus would come out of that? It would be X and X. Let me explain this to you. When one H and 3 breaks down, you get one H plus and one N3 minus. When X breaks down here, you get X here, X here. This ratio has to be maintained. This number has to be maintained, and that's what we're seeing here. Now I can set up an expression for Ka. Ka equals to X squared divided by 0.400 minus X. With this problem, I'll have to give you the Ka value. This Ka value, let's assume that Ka value is given, and that value is 1.9 times 10 to the negative 5. So you can write down here 1.9 times 10 to the negative 5 equals to X squared by 0.400 minus X. Next, you need to solve the problem for X, because that would give you H plus concentration, and then we can get percent ionization. Now I want to caution you that in most problems, over 90% of problems, you can ignore X from the bottom and solve in an approximate method. But if X, calculated X value is more than 5% of this number, then you'll have to do it in a longer method, which is by solving a quadratic formula. In this case, it happens to be that case where X value will be greater than 5% of this number. Though if you have a calculator, like engineering calculator, you can program it in such a way that it will give you X values. Otherwise, you need to solve it by any, this is like any algebra, you multiply and then simplify, and you should write it down like this: X squared plus bx plus c equals to 0, in that form. So this is going to be the coefficient of x squared, this will be the for x, and this will be the rest without x's. And for this formula, there are two x values, minus b plus minus the square root of b squared minus 4ac divided by 2a. In chemistry, we would not deal with negative numbers, so just ignore the negative. So two minuses in here would not work because concentrations are always positive. Again, I was telling you that in over 90% of the problems given in your book, you don't have to solve by this method. Maybe in small percent cases, like in this case, you'd find that x value would be more than 5% of this number. So to be more accurate, you'll have to solve by this method or using your engineering calculator, scientific calculator, you'll be able to solve it. Now let's give you the answer now. X value, that's what we got, is 2.76 times 10 to the negative 3. You should try this both ways and you see whether that's the case here or not. Now in case, of course, in case that you find that x value, I don't remember whether our value is more than 5% or less than 5%. In case it's less than 5%, you can get your solution by ignoring x from the bottom and solving for x. So this is the answer that I got for x, which is H plus. And the percent ionization will be given by x over 0.400 times 100. And that will give you 0.689%. So you can see that this is more than, in this particular problem, this is 0.689. So 0.689% of this acid breaks down into H plus and N3 minus. So that's the answer to this question. So make sure you try yourself and see whether this x value that you calculated is more than or less than 5%. I think it looks like it's less than 5% of that number. From this value, I can say. Okay, now we're going to do practice problem number 12. Now, solutions, salt solutions and pH. Salt solutions and pH. I'll give you a number of salt solutions. Again, this is just by observation. In most cases, you'll be able to answer it right. Say I have sodium chloride given and ammonium nitrate given. And we made a solution in water, and we want to know whether it's going to be acidic, basic, or neutral. Let me add one more, calcium bicarbonate. Now you can split that into acidic and basic part. Every salt would have one part coming from a base, another part coming from an acid. So in this case, just stick in, to get the basic part, add OH. Since sodium is plus 1, there'll be 1 OH minus added. So you get NaOH. This is HCl. So this is a strong base. This is group 1A hydroxide. This is a strong acid. So when you have a mixture of a strong acid and strong base, neither is going to be dominant. So it's going to be neutral. So NaCl would show pH equals to 7. There's no change in pH value. Again, ammonium would have +1 because nitrate, NO3 is -1. So this is NH4 is +1. So that would be one OH that would be bonded there. That would give you NH4OH. And this will give you HNO3. We all know NH4OH is not like group 1A, 2A hydroxides. So this is going to be weak base. This is a strong acid. So you expect acidic solution. Acidic means pH less than 7. For calcium hydroxide, again I can split that into basic part. Calcium, this is 2 underneath here. That tells you calcium is +2. So calcium +2 means there will be 2 OH minus that will be bonded. So that will give you CaOH2. And this is coming from carbonic acid. Just stick in one H plus. And you don't need to worry about this 2. That means there are 2 such H2CO3. But this is the acid part. This is the base part. This is a strong base. This is weak acid. Carbonic acid is weak acid. So reaction is going. This is going to give you a basic solution, and pH will be greater than 7. Now, practice problem number 13 would have a question on conjugate acid and base. So let's write down conjugate acid and conjugate base. Say I'm giving you this particular problem and I'm asking you to get conjugate acid of this compound. So in order to get the conjugate acid, you need to add H plus. So plus H plus, and that will give me H3PO4. So this is going to be conjugate acid of this given compound. If I want to get conjugate base, keep in mind, so in order to get conjugate acid, add H plus. In order to get conjugate base, take away H plus. So I get HPO4, 2 minus. That's going to be the conjugate base of this compound. So make sure you understand problems like these. There will be simple questions like these, which would take only a fraction of a minute. Next, we're going to go over practice problem number 14. Now, this one is a question on a strong base, pH of a strong base. Just like your other exam, I think second exam I believe, there'd be a question on a strong acid, weak acid, and a strong base and weak base, pH calculations or pOH values. So I selected this problem from the book 16.45 from Brown and LeMay, 12th edition. 16.45, the question is, you have 1.5 times 10 to the negative 3 molar strontium hydroxide is given. What is the pH value? This is group 2A. As you go down in the periodic table, those dissociate much better than magnesium. So magnesium doesn't give a strong base. Other members give strong bases. So strontium hydroxide would break down like this: SrOH2 would break down to Sr, just like calcium, 2 plus 2 OH minus. So initial concentration is given 1.5 times 10 to the negative 3 molar. At the beginning it didn't have chance to break down. At equilibrium all of them would break down. You get 0 here, or close to 0 there. Keep this in mind. When one of these breaks down, one of these compound breaks down, you get 1 Sr2 and 2 OH minus. if 1.5 breaks down, obviously you get 1.5 or same number here, but 2 times that number here. So 1.5 times 10 to the negative 3 here, 2 times 1.5 times 10 to the negative 3 here. For pH calculation, we're only interested in here, OH minus concentration. So that's going to be 3.0 times 10 to the negative 3 molar OH minus. And so I can calculate POH equals to minus log of OH minus concentration, which is minus log of 3.0 times 10 to the negative 3, and that gives me 2.52. That's POH. Now why POH? Because I have OH minus concentration. If I had H plus, then it would be pH directly. So in order to get pH, you need to apply that formula. pH plus POH is 14. So pH is going to be 14 minus POH. That's the value we already got. And 14 minus 2.52, and that gives 11.48. So this will be the end of our segment 1 for review 5.